Okay, this section, we're just looking at the variation of the pressure with direction. For example, let's assume that we have a cube under the water. We're just going to just analyze the distribution of the pressure and also the resultant force. You can see here the top at the bottom and also the bottom of the surface. Let's say they are like the horizontal plane, and the pressure is constant. You can see here, for example, from the top, it's like the same, like the throughout, like the surface from the top surface and from the bottom is the same. And but also from the side, we have like a distribution of the pressure increasing from the top to the bottom in here. So let's like you look at here, the pressure on the top is like a rho g h1. So for example, from the top, and from the bottom, you can just write here rho g h2 because the height is like the h2 to the water surface. And and obviously the force on the top is rho g h1 times the area of the top, and the force at the bottom is like a rho g h2 a. So the area and the force are from the bottom. So this is like the situations that we have. So because the h2 is bigger than h1, so the net force, the resultant from the force from the top and the bottom, is equal to the difference of the forces in here that we're just going to have, which is acting vertically upside or upwards. Why? Because the force at the bottom is higher than the force at the top. So rho g h2a minus rho g h1a. So if you can factor rho g and a, so inside the bracket we have h2 minus h1, and you know better, the h2 minus h1 is equal to the depth of the cube, that you can just easily write h2 minus h1 times the area. You can just substitute this one with the volume. And if you're just going to substitute volume in here, it's very simple that we can just get to the same formula that we just discussed before to just calculate the vertical force. So the F is equal to rho GV. So that's something like very interesting. So the vertical force for any kind of like the particle or any kind of like the body under the water, you can easily calculate rho G, which is that we know, and the volume of that body under the water. Okay, so if you're just going to take that one as like the more general shape, like not necessarily like the rectangular or like a cube shape, it could be like irregular shape. Let's say in this case it's like a sphere, so we can derive the same like a relationship. And by the way, just bear in mind the horizontal forces from the left and right, they balance out each other, so they can easily like we don't have like any kind of like the force, net force from left or right, but the net from the bottom and left, so the bottom can easily calculated based on this formula, and we can get to the same like the situations. So the rho GV can be applied to all of them the same as this one. Let's look at like with that kind of like the introduction, let's look at the like a buoyancy force. In other words, we can say this F is a buoyancy force which acts vertically upward towards like the center of the gravity of the displaced liquid. So for example, this F acts at the point B. For example, for this cube, this point is the intersection of the diagonals of like the cube, for example. So then, and this point B is called center of the buoyancy. So the amount of the F, as we learned here, is equal to the weight of the volume of the liquid displaced, or the volume of the water displaced if the liquid is water, and is equal to rho GV. So we need to just calculate the volume of that displaced water, for example, and to calculate the buoyancy force. So this kind of like the buoyancy force was discovered by the ancient scientist Archimedes, and this kind of like a principle is called Archimedes principle. So this is like the Archimedes principle and the buoyancy force and the center of the buoyancy. Let's look at like a situation of something, a cube floating on the water. So let's look at this and see the situations. If, for example, we have like a cube like here, which is floating, for example, we have two forces. If you just look at the situation of the forces, one is the weight, the unit weight of the cube materials times the volume, for example, that is the weight of the material. So the unit weight of the cube times the volume. The unit weight of the materials is like a rho SG, for example, and the volume is denoted by V. For example, W, or the weight, is equal to rho SGV. So that's like, you can just say this is like a based on the newtons. And also we can have the buoyancy force, as we learned it here, is acts vertically upwards. However, the weight acts vertically downwards in opposite direction. So the weight, so the buoyancy force is equal to the weight of the liquid displaced by the cube, and is calculated by rho GV. And the rho is the rho of the water, for example, or liquid. G is like a 9.81, is the same, and V is the volume of the water or liquid displaced. So just bear in mind. So the two V's are different, okay? But depending on the situation, if the W is greater than F, for example, the balance is that this W is heavier than the buoyancy force. Then the cube would sink definitely, okay? Because that's kind of like is bigger than F. However, if the W is smaller than F, for example, if the V here is the volume of the cube for both like the formula, if W is less than that, the cube is always floats and under the water, for example. The good example of that is a cork. The cork all the time is like a floating of the water. And if the W is equal to the like the F, we have like the partial stability of the like the body, so neither float or nor sink. So we can say like the body flows with a constant depth of immersion. So we have something like the we normally don't have this situation. We normally got to the situation either this one, W is greater than F, or W is less than F, that we say like there's a floating. Based on the second like the relationship, once we have the W weight is less than F, we can just calculate and make all the rules for like the boating and shipping and everything. So we're just going to discuss about that in further details.